Oh, I hear it. If you guys do have the YouTube open. Hi, everyone, and welcome to Ignite Virtual. So big thanks to all of you leaving the world behind and tuning in to hear cool stories of research tonight. I'm Mark Richardson, I'm your host. I'm the Education and Outreach Officer for the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. That's a collection of scientists, universities, and research labs across Canada trying to uncover some of the biggest mysteries of the universe by looking at some of the smallest things. So I'm here in Kingston tonight, Ontario, and I'm an astrophysicist by training who studies how galaxies form and change over time. And I love these opportunities to share with the wonders of research with each of you. So these events are seen as opportunities to share with everyone at home how amazing and exciting and useful science is for how we overcome big problems, be it pandemic, or climate change, or cosmic radiation, or human injuries. And so I'm really happy that even during COVID, we're able to have these events and people are joining in live or after the fact. To all of you joining in, not live, hello. So hello to everyone joining from home, whatever lands you call home. So for me, home is the lands of the Cataraqui, now Kingston. This is the traditional land of the Anishinaabe and the Haudenosaunee peoples and many indigenous peoples before them. And I'm truly appreciative that we are all able to learn tonight from our respective homes. Personally, as a settler from Halifax, Nova Scotia, the traditional land of the Skin Dressers district of the Mi'kmaq, and once the home of the racialized community of Africville, I recognize that my ancestors were complicit when these people had their access to these lands removed. Now, as an astronomer, someone who revels in the wonders of the land, the planet, the skies, and the universe, I recognize that this science relies on facilities that use traditional and sacred lands of various indigenous peoples. Peoples who have a voice to add to this science and who should be gatekeepers to their spaces. So I reflect on these aspects of my identity and how they afford me certain privileges in my academic life. So to all of you, I urge you to think of the connection you have with the land around you and the gift we have to learn wherever we are. And so I actually encourage you after tonight's event, maybe to explore the website whos.land. And I'm showing it here. It shows you all the different kind of lands and territories that belong or that were inhabited by different indigenous peoples, and learn about those past people who lived where you live. So moving forward, let's reflect and work towards the decolonization of these spaces to make them ones of friendship, love, and access to all those in our community. All right, so the plan tonight is simple. We have two groups joining me today or tonight to talk about their research and the big questions that motivate it. But first, I would like to welcome Dr. Tony Noble to share his video. Tony is the scientific director of the McDonald Institute, and it was him that started with the partnership with the university, Queen's University Relations, to make Ignite a reality. And so, Tony, I'm wondering if you could say a word or two on Ignite.
Yeah, sure. Thanks, Mark. Yeah, so as Mark mentioned, my name is Tony Noble, and I'm the scientific director for the McDonald Institute. And at the McDonald Institute, you know, our primary goal is advancing science, and in particular, the science of astroparticle physics, which means we're trying to understand the properties of the most fundamental particles in the universe, and at the same time to understand their role, you know, what they play in astronomy and in cosmology, in shaping the structures that we see and the evolution of the universe. And so that's quite particular, I guess we could say. But one of our goals is to share the research stories with our communities. And what we decided to do was to partner with Queen's University to not only capture our research stories, but to highlight exciting research across all disciplines, to bring communities together, have an opportunity to chat and so on. And normally these lectures would be actually interactive and in person. We get all kinds of excitement from student clubs and from other presenters to bring pieces that you could interact with and talk to other people and really get a feeling for what's happening at Queen's across our campus. And so we're hoping that eventually we get back to being in person, of course, but we still hope that these lectures serve to engage and inspire the public, and in particular to ignite interest in future generations of researchers. And I think you will greatly enjoy the taste of research that we're bringing to you tonight. I'm looking forward to it greatly, and I'll turn it back to Mark.
Thanks, Tony. Yeah, that's I think that's I really look forward to the time that we can come back together and be in that space and really being able to have these conversations. I really like that YouTube. I think our feed might be lagging out. Cool. I really appreciate that YouTube is allowing us to have these conversations and commune with each other. But the nice thing about being live is we have lots of opportunity to show demos. And so I'm really thankful to the speakers that we have tonight. They're actually going to show us some behind the scenes footage of where they actually get to do their research in some pretty unique places and labs in the world. But stay tuned for that. And I guess to get the ball rolling, I really want to welcome our first speaker tonight. So our first speaker is Dr. Kevin Deluzio. Kevin is the Dean of the Faculty of Engineering and a Professor of Mechanical Engineering, and he leads the Human Mobility Research Laboratory at Queen's University. Kevin has been a faculty at Queen's since 2006, and prior to his appointment as Dean, he was the head of the Department of Mechanical Materials Engineering. So Kevin was the founder and director of the Dynamics and Human Motion Laboratory and associate professor in the School of Biomedical Engineering, cross-appointed actually to the Department of Surgery at Dalhousie University back in Halifax, where I'm from. And Kevin is a professional engineer and is internationally recognized for his research in human motion and orthopedic biomechanics. Kevin has served on the executive of the Canadian Society for Biomechanics, as president of the Canadian Orthopedic Research Society, and on national grant review panels. And so in 2018, actually, Kevin was named a fellow to the Canadian Academy of Engineering. So Kevin, I think if you could share your video, it's really great to have you joining us with us tonight. I look forward to hearing from you and your colleague, Dr. Elise Laende, and maybe some of the behind-the-scenes views that you're gonna give us.
It's thrilling to be here. It was I really enjoyed it. It was a great welcome, and I thought the map that you had on there I hadn't seen that before. What a fascinating way to picture North America.
Particularly, I think when we're all joining from different areas, it's nice to put it in context.
I'm gonna use that. That was beautiful.
Cool. Well, I encourage you to share your screen and start us off.
And hello, everybody. Here I am. Okay, now give me a minute to make sure that I do this correctly and share screen. Hit the button that says share screen and choose the right one and share. Okay, does that look okay? Perfect. Okay, excellent. Well, welcome everybody. This is biomechanics with me, and there's a picture of a better looking me, I think. But it's a privilege to be here and to share a snippet out of the world of biomechanical research, and with a focus on what we do here at Queen's in that area. Queen's has a long-standing history of expertise in the area of collaboration between engineering and surgery that finds itself in this world. And I want to begin with asking you a question if you've thought about joints as organs. Now, when we think of organs, we tend to think of vital organs, our lungs, our heart, kidney. When we think of joints, we tend to think of a connection between two bones. And we simplify the anatomy. And we may think, for example, in the knee, we may think of it as a hinge joint. But I want to posit to you that joints are way more complex than just two bones. It's a combination of ligaments, soft tissues, cartilage, synovial fluid, nerves, muscles, and they're joined in a unit to serve a common function. And if we look at it that way, definitely the knee joint satisfies this definition of a joint, of an organ that you see on your screen here. And if we think of the function of a joint, well, the function of the knee joint is to facilitate movement and transfer forces. Now, the knee is located between two of the largest bones, or you could think of them as levers in the body, the tibia and the femur. And they withstand massive forces. Your knee joint experiences forces of 2 to 3 times your body weight with every step you take. And we've been fascinated about this for some time. And I'll point to, Giovanni Borelli, who was actually a student of Galileo. So we had to get an astrophysicist link here, who was one of the first scientists to consider the forces in motion produced by animals and relate them to machines. And in many ways, when we look at his work, he's considered the father of modern biomechanics. Now, what is actually biomechanics? Well, this translation of a biological organ system to a mechanical system to study the forces that act on the biological system and the effect of those forces in producing motion or stability is the field of biomechanics. And I'll take you back when I was a young engineering student many years ago, actually here at Queen's University. Biomedical engineering was an emerging field. And I was very interested in the idea that we could apply engineering skills to understand human function. Okay, so let's go back to the heart or the organ. If we look at, we're going to assess the functional, how an organ operates, and we're doing this with the heart. Well, the heart's a functioning unit. So we look at pulse, blood pressure, ECG, and other mechanisms or other tools to interrogate the function of the heart. But we do this while the heart is working. And if we contrast that to the knee, the tools that we use are static x-rays, right? X-rays provide wonderful views. And here you see a magnetic resonance imaging image of the knee, or an MRI, that again is exquisite in terms of the detail. We can see soft tissue, you see all kinds of wonderful details. You see the muscles there, the bones, the cartilage. CT scans are another way to do this, but all of these imaging techniques and the information we use to evaluate how healthy the knee joint is done while the knee is at rest and not performing a function. So when we think about vital signs, there's an argument that could be made to include gait, or could the way you walk, which is referred to as your gait, be considered a vital sign of our musculoskeletal system? So gait, well, it's the way an individual walks, right? That's the pattern of movement. And although we don't tend to think too much about how to walk, we do it without thinking, it is really a complex function requiring balance, coordination, smooth transfer of functions. Gait is also a learned skill. There's been some fascinating work done when you look at development, and humans without sight don't naturally learn to walk. Humans learn to crawl quite naturally, but to walk is the sheer determination of seeing someone walk, usually one's parents, and then deciding to do that. And if you've ever looked at an infant starting to walk, it's an incredibly unstable process that is driven more by the personality of the child than real natural ability. And it is that therefore individualized. You know that you can recognize somebody by the way they walk. You see, when we used to be on campus, because often I'd look across campus and I'd recognize a colleague purely by the pattern of their motion. It's repetitive too. And there's a rich amount of information in this. But the question is, well, how do we quantify gait? And if you look at the slide we have there, you have things that we can divide it into phases, when the foot is on the ground, when it's in swing, and others. But how do we get rich information from this? Well, the quantification of human movement, again, we've got a little bit of a historical timeline going on throughout this talk. And the quantification of movement started in the late 1800s. And it's really interesting. If you look at this images on the left, it started with a bet that Leland Stanford had posed. And yes, it's the same Stanford that founded the university. And back in 1872, he posed this question of whether all four hooves of a horse were off the ground at a single instant in time during the gallop. And the most widely held belief was actually that if it occurred during the outstretched time when the legs were forward and aft of the body. And if you look at these images really closely, you can see that no, that's not when it happens. But yes, four hooves are off the ground, and it happens when the four legs are underneath the horse's body. This development of the technology to capture these images, that was also this technology, same technology that a man named Muybridge was developing in North America, and Etienne Méret was developing in France. And it was really the birth of modern cinematography. So we can thank all our movies to the fact of a bet. Well, more importantly to my world in human gait, it was about 20 years later with the work of two German scientists, actually a physiologist and an engineer, Braun and Fischer, who did the first gait analysis. Now, this is one of their human subjects, and he's got light rods that will light up as he walks in a completely darkened room. And if you can see the image of his face carefully, you'll notice that he's probably looking a little nervous, and that's because the electric connection is on the top of his head. They put a little piece of gauze there to provide some insulation, but I'm sure he was not comfortable during the whole transit of the experiment. So fast forward a chunk of time, and we do gait analysis or motion analysis way better now. Our subjects are much more comfortable. And it really has evolved into a precise science of identifying skeletal landmarks, i.e. like the hip joint here that is being pointed to, or the greater trochanter on the femur, where we mark the location of these landmarks on the skin surface, and then using special reflective markers there and specialized cameras, we can record the precise location of these landmarks in three-dimensional space to an accuracy of maybe within a couple millimeters, and doing this hundreds of times a second to be able to get movement. Now, if we now move ourselves into my laboratory, which exists at Hotel du Hospital, you should be seeing a video of a subject walking in the lab. And they certainly look a lot more comfortable than the subject that was in Braun and Fischer's experiment in 1893. And they're walking, you can see the markers that are attached to the subject. You can see as they walk over the floor, they're actually walking on specialized, special instrumented force plates to get the force. And what we're trying to do is capture the motion and understand what's behind the motion as people perform activities of daily living. So this would include walking. We can also do things like stair climbing or walking up treadmill. And the idea is to see if there's information in the way we move that is related to the health of the musculoskeletal system and may suggest why some people get diseases like arthritis and others don't. Our particular interest in the lab is regarding osteoarthritis, which is now, here's a warning. I have an image warning on this slide. If blood bothers you, this is a dissection of a knee joint. So you may want to turn away from the screen before I take this off, which I'll do now. So our joints, just like other organs, well, they can fail. And osteoarthritis is a joint disease characterized by the progressive deterioration of joints. There are many causes of OA with a common endpoint where the joint can no longer function. So if you look at the image on the left, you see this is you're looking at the top of the femur on the top, and at the bottom is the top of the tibia. And there's your knee joint exposed, and you can see the white cartilage that looks quite healthy on the left side and would reflect what you may have seen when you've opened up a chicken bone, for example, at the joint. And on the right, you can see that white material that is worn away. And once that's worn away, the knee joint becomes incredibly painful. So osteoarthritis is very common. It affects a large portion of the population, and it disproportionately affects women. It affects life incredibly in the fact that it limits what we can do. And because of that, it leads to higher risk of other comorbidities that people can develop. And the important thing is OA has no cure, and even the causes of osteoarthritis are unknown to some degree. And without a cure, we turn to total joint replacement as the biggest treatment for this. And here's a cartoon of a joint replacement, which is a metal implant that is put in the knee joint after all the cartilage has been cut away and removed. And this is a major surgery, and I'm looking forward to the time when we can develop better treatments for joints. But it should be emphasized, this is an incredibly successful surgery from the outcome of the patient, because it gets rid of the pain. So it's actually, if you look at patient satisfaction, it's second only to heart surgery. And that's because if you come into this hospital with needing heart surgery, you are going to die, and you don't. So you're pretty happy. You rate that way over on the right-hand scale. I'm very happy. It's next to that, it's knee joint or hip joint replacement because the pain is gone. But the function of people is still quite limited. So we look at osteoarthritis. What can we learn about what causes it and how can we intervene somehow? Well, primarily, osteoarthritis is a disease of mechanics. And this was evidence of this came out starting in the 1950s, where we looked at things like surveys and others where we found that, well, jackhammer operators got more arthritis in elbows than other people. And people that did heavy work got it more than people that had a sedimentary lifestyle. I can tell you as a mechanical engineer, the idea that this was a disease of mechanics raised a lot of interest in me as a young researcher, and it's really formed the basis of my career in research. There was also some really compelling experimental work that was supported by this as well. This was done back in the 70s, where it was determined that it wasn't just the load, the magnitude of the load that was applied to the joint, it was the frequency of the load. It was whether how the load was sustained. It was the pattern of behavior in that load. And that really is, if you look at one of the most repetitive things we do as humans, well, walks, thousands and thousands of times a year, we're putting 2 to 3 times body weight through our knees. So we can measure this in the lab. And here you see us using our motion capture system to measure, again, in vivo function, how the body is functioning while we're performing activities of daily living. And we can measure things. Highlighted here is the knee joint angle, and you can see that in the skeleton as it changes, this joint angle changes, and therefore it changes. This is what you see in the graph is I think about 50 or 60 people that are healthy joints and their joint angle as it goes through the gait cycle superimposed on a group of subjects with arthritis. Now, one of the things that our research group brought to this area was the application of pattern recognition techniques or machine learning techniques to identify patterns in these data to be able to discriminate or classify subjects as healthy or osteoarthritic depending on their gait, and those features had meaning related to, some of them actually were related to things like disease progression that we found. We've added a third tool more recently, and that's musculoskeletal model, or really computer models that are driven by the experimental information that we gather on the subject's movement, but have a level of detail in them where the muscles are modeled and the joints are modeled as well. So we can estimate things like the joint contact force or the muscle forces that we think are related to things like arthritis development. And we can ask a lot of what if questions. And I'll leave you with one example where we applied this on the treatment of osteoarthritis. So one of the more common early treatments that tries to get people to avoid a knee replacement is a knee brace. Surgeons will prescribe a knee brace for people with early osteoarthritis, and these have varied degrees of success. Sometimes they work and they relieve pain, other times they don't. We really don't know why they work or the question of who are they best suited for, what kind of patient. So we used our techniques in the lab. So here you see on the left where we were able to get the musculoskeletal model, monitor people that had arthritis wearing the brace and without the brace, and include the mechanical effect of the brace in our musculoskeletal model as we did this. And the research showed that, yes, the brace was able to unload the knee joint, but not one of the reasons we proposed was where people hypothesized, maybe it was because the brace made you walk differently because you had a brace on, so you used your muscles differently. Perhaps other effects of, again, you had some feeling of your knee joint because of the extra stuff around your knee joints. You had more sensory feedback from the knee joint. But really what we found was two things: that the primary reason for the reduction in the joint force was because of the brace, the mechanical effect of the brace. So that can inform how we design the braces. And furthermore, we found that we could predict who the brace would be more effective on. Now, this was an initial study of small subjects, of 60 subjects that were hard to get at. So this hasn't been translated into clinical practice. And one of the challenges of translating what we learn in the lab into practice that affects you and I is the scale and the size of the studies that we can do. And one of the limiting factors to that is the technology, the specialized lab we need to affix those specialized markers and such. So we've been playing with a new tool now, and to be able to get more people into the labs and be able to do this less invasively. So the new technology that we're invested in is markerless motion capture, which uses, again, regular cameras and artificial intelligence learning techniques to track and identify anatomical landmarks as people walk wearing their natural clothing in natural environments. Now I'm going to pass it over here to my colleague, Dr. Elise Laende, who is my postdoctoral fellow working in HMRL. She did her PhD actually in Halifax at Dalhousie and has spent a great deal of number of years doing research within a clinical facility within a hospital looking at orthopedic research. So I'm going to pass it over to you, Elise, and stop sharing my screen.
Okay, I'm hoping that that's showing up now. Great. Thank you for the introduction, Kevin, and thank you, Mark, for inviting us to present today. So as Kevin mentioned, I'm going to give a quick overview of the Human Mobility Research Lab and talk a little bit more about some of the technology that we've been developing. So this is a rendering of what the lab looks like overall, and I'm going to go straight into a little video virtual tour of what it looks like when you're inside our lab. So it's about 3,000 square feet of lab space, and we measure human motion from activities of daily living to high performance sporting activities as well. And we have force plates embedded in the floor, as Kevin mentioned. That's one of the pieces of technology that let us do this. We also have this instrumented treadmill that we can incline to make running more challenging for runners, and it also will measure the forces. It has some embedded force plates. And then over here, we can see the high-tech, expensive infrared camera. Okay, and so those cameras that we're showing there, they allow us to track the markers on the individuals. So you can see how those markers are tracked, and then within the biomechanical modeling, we can build a full skeleton and see what's happening within the body. We also have EMG technology, so we can actually measure muscle activity as well. So that's a little peek into what the lab looks like. Hopefully that gave you an idea of the kind of work that we can do in that space and what we've done typically in the Human Mobility Research Lab. And I'm gonna go a little bit on a sidetrack here and just give some motivation as to why I'm personally interested in biomechanics. It's a field that I've been involved in for a long time. And one of the things that I think about when I'm doing this research is my friend Janine. So she's one of my best friends. We go way back to grade 7. And this was the last time I was able to see her in person when I was visiting her and her family. I was there with my little one as well. And this was us just a few years earlier, well, many years earlier. And this was after she had had her ACL reconstruction surgery. This was after she tore her ACL skiing as a teenager. So ACL injuries are fairly common in young athletes. They affect about 1 in 60 young athletes. And the ACL, or the anterior cruciate ligament, connects the thigh bone, the femur, to the shin bone, the tibia. And ACL injuries occur most often in sports in non-contact situations. So during soccer or basketball games when someone just lands the wrong way. What's interesting about ACL injuries is that they tend to affect female athletes significantly more than male athletes, 5 to 8 times more often. And unfortunately, they are linked to a risk of developing osteoarthritis, which is pretty significant, the increased risk. And so certainly this was unfortunately the case for my friend, and she ended up developing severe knee OA in her 20s and 30s. She was in constant pain, could only walk for very short periods of time. And obviously this seriously impacted her life, as she had 2 young kids and she was a teacher and she was coaching basketball, and this was a huge burden. So her surgeon recommended that she get a knee replacement quite early. And that's in fact what she went on to do. And so when I think about this, I think what's important to recognize is that she isn't represented in the research that we've done to date. When we look at OA patients, they're usually in their 60s, maybe their 50s, not in their 30s. And while this is an unusual case, definitely it's not unique. And we need to better understand who is at risk of ACL injuries and later developing OA. And we need to see if there's anything that we can do to interrupt this trajectory that she unfortunately ended up going down. So to do this research, as Kevin alluded to, I think that one of the things that we need is better tools. And I'm hoping that these better tools will allow us to study individuals over the length of their lifetime and to study much larger numbers of individuals to better understand these diseases. So we'll talk about that a little bit. So not to badmouth marker-based motion capture, we have learned so much from it, certainly, but it is very challenging to perform, as we hinted at. And some of the reasons for that is the really specialized environment that it can be performed in, and it's really time intensive. To put these markers on a subject and to do a full data collection often takes around 2 hours. It's also fairly invasive. You're palpating people to find their bones underneath their skin. And the markers that we put on the body, we try to represent what's happening at the bone, but as you can imagine, on top of your skin, those markers are moving relative to the underlying bone. And we're not really sure what those errors are on an individual level. We know what the range is. And putting those markers on are also very dependent on the individual who does the data collection. So we're interested in markerless motion capture. As Kevin mentioned, there's a number of different technologies that allow us to do markerless motion capture, such as depth sensor technology. This is analogous to the Microsoft Kinect product. That's a type of depth sensor. You can also use inertial measurement units, which are similar to what you would have in a smartphone that allows you to do activity tracking. And then there's also video-based data. And this is something that we're interested in investigating. And we're looking specifically at the Thea markerless system. So this is a video-based markerless motion capture system that was actually developed locally in Kingston by 2 former graduate students from our lab, which is always exciting to participate with. And this technology works by using machine learning. So how this was done in the development process was that upwards of 500,000 images were used, and all of the points on the body were manually labeled. So many users were pointing and saying, this is the shoulder, this is the hip, and training an algorithm to recognize those points on the human body on its own. And so what happens is that once those points are identified in every single camera view, a 3D location of each point can be determined, and this allows us to fit the biomechanical models and do a gait analysis similar to what we've done in the past with marker-based data collection. So when we do a data collection in the lab using the markerless system, this is what it looks like. It's quite different to how we did the marker-based, because as you can see, the subject is participating in their own clothes. We are using just off-the-shelf video cameras. So they're very small. They're about the size of a GoPro camera. They're about 1/10 of the cost of the marker-based cameras. And what we're able to do is collect in any environment. So we don't need the specialized lab space that has special lights and no reflective surfaces, so nothing interferes with the infrared cameras. And now we can take data collections to participants instead of requiring that they always come into the lab to do data collections. And so now we can study athletes in game situations and patients in clinics and hospitals. So some of the other advantages of the markerless system are that we can capture multiple subjects simultaneously. So this is great for looking at athletes in games. It also means that if someone has mobility issues, we could have someone helping them or assisting them while they walk. It also means that we can collect data outside, which we've certainly never been able to do before with our marker-based data collection, and that offers a lot of potential opportunities. And importantly, during the current situation, this is completely contactless. We've actually done data collections where the researchers were in a separate room and were accessing the computers to control the cameras remotely. And by having participants in their own clothing, we've significantly reduced our data collection time. So we've gone from about 2 hours to about 5 minutes to collect the same type of data. So how do we know if this works? Well, we've tested it against a couple of different existing technologies. So this was a pressure sensitive mat that is used in clinics to measure stride and gait speed. And we did a head-to-head comparison. And we found that the parameters that the clinicians are interested in, we were able to measure equivalently with the markerless system. We also did a head-to-head comparison with the marker-based motion capture. And so this little video shows you what the two models look like superimposed on each other. So we actually measured 30 subjects and we recorded them with both the markerless and the marker-based at the same time. And then we're able to see that the biomechanical parameters that we're interested in that have been used in the past to study OA, we can capture with this markerless system as well. And this level of biomechanical data is not something that we can really get with something like a Microsoft Kinect product that only has one camera. So by using those 8 cameras, we're really getting high-level biomechanical data. We also have some other applications of this technology. We're currently working with Dr. Stephen Scott, who's in neuroscience, to see if we can use markerless motion capture and apply it to other conditions such as stroke and post-traumatic brain injury. And what we're hoping is that we can use this type of technology to provide more sensitive clinical assessment tools than what are currently used. So something like a timed up and go, which you saw the participant do there, where they rose from a chair and turned around and sat back down. It's typically assessed just the total time it takes someone to complete that, but we think there's so much more information that we can capture with motion capture that tells us about how they perform it. And same thing with balance. So instead of just saying, yes, they could perform this balance, we can actually quantify the strategy that they used, how they shifted their weight, and hopefully we can provide more sensitive measures for clinical conditions and allow us to better evaluate interventions and medications. So we have lots of opportunities with this markerless data set, this markerless data collection system. One of the things that I think can be really important is the longitudinal data analysis. So bringing patients back multiple times, maybe even over their whole lifetime. And because we've removed the effect of an individual researcher putting the markers on, we think we're going to get more repeatable data that we can use to evaluate changes in an individual over time. We also have reduced the difficulty of doing this kind of research. And so we think we really have the opportunity to expand the sample sizes of our data, partly because it's less expensive, it's more flexible. We can take the research to the participants instead of making them come to us. And we also hope that we can reach new patient populations because we think that this type of data collection really reduces the burden on the patient. And so we hope that this technology, this new technology that we're investigating right now, will allow us to perform biomechanical assessments in new ways over the course of an individual's life and in much larger populations than ever before. And we hope that this type of technology is actually going to allow us to look at problems like ACL injuries in young athletes and better understand the implications over a lifetime. So thank you very much for your attention.
Thank you so much, Elise and Kevin. Kevin, I welcome you to show your video again, and I don't know if we want to keep that video playing. It might spur in some questions, but spur on some questions. But we've had plenty of questions already, and so I would like to take this opportunity to ask you some of them. So let's see. So Nancy Lorimer said, is there ever and this is, I think, directed at you, Kevin, is there a sound that can be associated with OA of the knee? For example, she finds sometimes she hears a grinding noise and she's always wondered.
Definitely, there is yeah, absolutely. That can be. There's a lot of reasons why you can hear. And again, I'm an engineer, right? Not a clinician, but absolutely, you read in the literature about all kinds of symptoms like that that would relate to either sounds or feelings within a knee joint. Often it's hard to capture those accurately. But yeah, you can definitely get that feeling of something or some sounds even that can occur. Yeah, absolutely.
And then Zachary Wima asks, and sorry if I mispronounced your name, are reoccurring shin splints likely to end a running career?
Elise, you want to take that?
These are the engineers speaking. As I've been told many times, we're not the useful kind of doctors.
Yeah.
I don't know that much about shin splints. I would suggest that you talk to a physiotherapist for that one. I think in general, get it looked at, don't overdo it, and it's probably not the end. Kevin, any ideas?
No, exactly. And I think pain is always a good indication from your body, but it's exactly those kinds of things that we hope to be able to analyze within the work that's going on here at Queen's in our lab and in other labs as well. There's a colleague, Professor Rainbow, who has a lab adjoining this one that is actually using high-speed X-ray to look inside the joint, where information like that we may be able to tease out.
And I was curious if you have this quite impressive image of an OA knee versus a regular healthy knee. Besides presumably the patient being in a lot of pain, I'm curious if the X-rays or the MRIs, those other tools that are used for understanding knees, what does that kind of tell you? How does it reveal that OA is present?
Great question. I know Elise has some things to say on this one too, because we've got a lot of information. So you can have it's quite variable. So you can have a normal looking X-ray. So your X-ray joint looks just fine, and yet you can have quite severe arthritis, and because the X-ray doesn't pick up on the soft tissue damage. And you can also have an MRI or an image that shows the cartilage and shows focal defects or problems with the cartilage, and a patient who is able to function just fine. And that's the real issue, is they talk about and pain, which is the symptom. People get a knee replacement not because of the quality of their X-ray or subject. They get a knee replacement because of pain. Now there usually has to be some corollary in the X-ray, but it can be it can be quite heterogeneous. Elise, because you got lots of experience in this.
Yeah, I worked with orthopedic surgeons for a number of years, and they would never use an X-ray in isolation. Yeah. So they would probably not operate without evidence of damage on an X-ray, but they wouldn't use it alone. And so surgeons will ask patients to walk, and they do essentially a visual assessment. And part of what we're trying to do with this research is quantify that. So surgeons over a career have figured out they can recognize the pattern of poor function in gait. And what we're really hoping is to provide more objective tools that capture that subjective ability that surgeons have developed over a career, and to provide it.
Some of the things we've seen in that are that the early signs, the things that change first, aren't the things you can see. People maintain a naturally looking gait as long as they can, but we see changes in other biomechanical features of the way they walk that you can't see, things to do with forces. Of course, you can't see forces that predict progression.
And there was a bit of a related question from Eduardo Reyes, who was given the differences between people, the differences in their clothing or whatnot, how did these methods that you're showing, Elise, how do they account for like slight skeletal anomalies or just variations between people? Do you account for that? Is there some kind of uncertainty that's come out, or is this really good at getting the skeletal structure?
Yeah, so it's something we're actively investigating more deeply. So it was trained on 500,000 images, and those are images not from our data collections, they're just images from the internet. And so the goal was to try to get as wide a variety of individuals, in different situations in different clothing. So what we're hoping is that it is not sensitive to those differences, but it's something we actively need to quantify and understand. And what we do hope is that even if it's not quite as accurate, because we're able to collect so many more patients, we can sacrifice a little bit of precision because our sample sizes are so much larger, and we can study a much more diverse population. And then that might actually allow us to draw more important conclusions than we can the way we're currently doing data collections.
So cool that you have that such a big data set you can work with. I guess that's the internet. So there was a question from Matt Webster, who was speaking about somebody who broke their leg and had a metal plate put in the leg. And so Matt was curious, like, in the if variations in the gait that result of those kind of inclusions do show up in this kind of model. Like, is it able to say, like, something is weird about this person, they must have a giant piece of metal in them?
I think what we can do is detect changes in gait, but not necessarily their cause unless we've got enough information in that. So we've spent decades building the database about features that we recognize because of arthritis. So we're very good there. And we're good at being able to detect changes. So if there was a metal plate that led to a limp or a restricted range of motion in any way, we definitely kind of get at that. But if it's subtle, no way. We'll be able to tell, this is the cause of that.
I see. And there was one last question, I think, for now, although I believe you guys are both sticking around for a bit. So if there's more questions that you think of between now and maybe while you're listening to the next group, feel free to put them in and we can revisit them. But the last question I have is, I'm thinking like Hollywood. You have Andy Serkis doing Gollum or doing King Kong, and the marker-based technology is what comes to mind. Do you know, are movies now going to this kind of model where they don't need the markers anymore?
They will chase this. So there's many people that are doing this, and that's one of the huge limitations. It's actually one of the points of pride of the biomechanics community is that one of my colleagues was part of an Academy Award for the work that they did in Lord of the Rings, which had to do with this technology. So and that's helped promote it. But yeah, you think of one of the major limitations now is putting those markers on the specialized clothing and everything else. So yes, there are many people in the world, and some of the challenges or some of the things that they want for Hollywood production or for game production is different from biomechanics. So the tools may be a bit different, but they'll be marked. I'm going to predict that within 10 years, we won't see any markers in it.
I'm going to lie. There was a question that came up. I encouraged one last question, and it's from Nancy again. And I think, Elise, maybe we didn't show a video today, but I know that you have information on this. But can you see this technology being used in children as a baseline for maybe growth plates or other issues?
Yeah, absolutely. There's no reason it can't be used on children. I think my video stopped playing, but it was playing, and we did test it on the nephew of one of our lab members who was 2, and it hadn't been trained on children, and it had no problem recognizing that as a person and doing the same type of analysis. So personally, I think that that's an excellent application, and I'm trying to get my little one in as many times as I can so that we can study these longitudinal changes over the lifetime.
Oh, that's so cool. That's so interesting. Well, thank you both for great talks and great discussion. And I'm happy you're sticking around. But at this point, I'm going to ask you to stop sharing your video. I'm going to bring on our next group, our next speaker.
That was a lot of fun, Mark.
Thanks.
Yeah, thank you. So again, thank you so much. It was fascinating to see what you guys were doing. But I would like now to introduce Dr. Nahee Park. So Nahee, you got your PhD from Ellingwood Women's University in South Korea in 2008, where you worked on estimating the elemental abundance of high energy cosmic rays using data, I guess, from balloon experiments. And you mentioned CREAM. And so this work got you so excited that I guess you were excited about both detector development and high energy astrophysics. And this led you to moving to the University of Chicago as a postdoctoral researcher. So there you continued your work on cosmic ray balloon experiments. You joined the VERITAS, very high energy gamma ray experiments to study the origin of high energy particles of our galaxy. And so to continue your research, you particularly looking for cosmic accelerators in our universe. Nahee, you moved to the University of Wisconsin-Madison as a John Buckle Fellow, where you worked on high energy neutrino astrophysics using data from the IceCube High Energy Neutrino Observatory located in Antarctica. And I believe we're actually going to get to see some of those images or some images from doing research in Antarctica, and I can't wait to see them. And so Nahee, you recently joined the faculty here at Queen's University. We're so happy to have you. I know that you are quite excited to be able to continue your work here exploring the dynamics of high energy particles in our universe with combined knowledge from many different types of cosmic messengers. I'm really interested to hear what are different types of cosmic messengers. So Nahee, it is a real pleasure to have you join us tonight. I look forward to hearing from you, and I know that your colleague Emma Ellingwood is going to be joining us shortly, but we're going to start by hearing from you. So welcome.
Thank you for the introduction, and thank you for Mark and as well as the McDonald Institute for making this opportunity happening for me. Should I share screen now?
Yeah, that would be great, and I will slick away.
All right, can you see my screen now? I'm moving on to full screen mode. Okay. All right, so hi everyone. I'm going to talk about high energy astrophysics, and I recognize that may not be the familiar term like previous presenters, so I'm going to just introduce quickly what is high energy astrophysics. So I'm going to here make light as examples because light is abundance around us, right? So we can see things because of the visible spectrum, but as you can see, the visible spectrum is a very small portion of the light, and the light actually extends as low energy, and the longer wavelength goes to the radio, and shorter wave goes to the UV, X-ray, and up to the gamma ray. So if you look at the basically the distance over how the wavelength is repeating itself, that's what we call this wavelength. And just giving you an idea, the pole to pole is about the 10 to the 7 meter wavelength. So that's about there. And the height of building is about a few meter. So that's the about FM wavelength. And the thickness of a hair is about IR wavelength, the length of it, and the blood cell is just about just a wee bit longer than the red light, and the molecular is much smaller, so that's about the wavelength of the X-ray size, and the atomic nuclei is the size of about gamma ray wavelength. So that may give you some scale, like how wide of a wavelength scale the light is covering. So where does a high energy astrophysics lies? In fact, the light continues. The light actually getting a shorter and shorter wavelength, and then that means a higher and a higher energy. So above X-ray, we call generally gamma ray. And when I say high energy, that usually starts as the GeV, that is about 3 billion times higher energy than the light we can see with our eyes. So that is what I call high energy. And what I am doing is basically studying this high energy, and particularly studying the universe by using all the things that has a high energy, higher than the, again, billions times higher energy than what we can see with our eyes. So why study high energy astrophysics? The reason why is because we can see a lot of different things. So just for example, looking at the hand, if you look at your hand in infrared, this is what you are going to see. Basically, you are seeing the variation of body temperature. But if you look at your hand in visible light, basically what we can see with our eyes, this is what you see in your hand. You would see nook and crannies over your hand and colors and everything. And then if you look at the hand in X-ray, now what you are seeing is not actually visible to your hand. You are seeing the bones of your hand, right? Just because the X-ray is so penetrating so that the skin, X-ray can just go through the skin, but it cannot go through the bones. So we are seeing the shade of X-ray. That's basically the bone picture that we are seeing. So it's the same hand, but we are getting the different information by looking at different wavelength of the light. It's exactly the same for studying the universe. So if you are looking at a particular stellar object, in this case, the remnant of an explosion of a star, if you look at the object in radio, this is what you are going to see. If you are looking at exactly the same thing in the infrared, this is the picture you are going to see. Visible looking like this, and then X-ray this is exactly the same object. So you can see that there's a lot of different features that you are seeing in the different kind of wavelength. So we are looking at high energy astrophysics because we wanted to see the universe in the high energy light so that we can learn new thing about our universe. So that was introduction for the high energy physics. Now, moving on to why am I started to get interested in high energy. So when I was entering the graduate students to get my PhD, I had to select which lab I'm going to work on. And I went to the one of high energy astrophysics lab, and they said that we are going to launch a detector, and then that will be on the space. And then we will study what kind of thing is happening in the high energy part of the universe. And I thought, oh, wow, that is very cool. I would like to work and then put my detector into space. So that's how I started. That was 2001. Just to giving you an idea, MS-02 was that experiment, and that actually launched in 2011. So in the end, what I actually worked on during my graduate school season was actually building a detector. I actually did a lot of work. And then in the end, instead of space, I went to the Antarctica and launched my detectors with a balloon experiment, which is pretty high up to 42 kilometers above the sea level, but not quite reaching to the space. So one day maybe I can launch to the space. But it was pretty fun. And then I got to meet a lot of interesting people and could build a lot of instruments. So I have no regret on the decision that I made. Okay, so what I'm studying, a lot of things I'm studying, motivation of all my studies coming from the cosmic ray. Cosmic rays are particles from our universe. So these are high energy charged particles originating in our outer space. And this was first discovered by Victor Hess in 1912. And I just wanted to remind you, in 1912, all this X-ray and radioactivity and everything was a very, very, very new thing. For example, X-ray was discovered 1895. And the radium girl, maybe you heard about it, that even didn't start it. So people didn't really know much about the radiation. We were just learning about it. And then what we learned was in the ground, when you are building an instrument, somehow the air is getting ionized, and it's much higher rate. So the question at that time was, is it because of the natural radioactivity of the Earth? And the simple answer has came up was that, okay, if it is coming from the natural radioactivity of the Earth, like radon, then if I go high up to the air, I should see reduction of the activity. So he put himself into balloon. Just to note that this was the first cosmic ray experiment kind, and then they were using balloon for this matter, and then he went up to the sky. And as you can see in this picture, at the time, the sky means that they could go up to 5 kilometers, and above that, it was just very, very hard because the air was too thin. And so if indeed this natural radioactivity was coming from the Earth, again, you would expect as you go higher and higher, you would see less of it, because you're going far away from the Earth. But instead, what Hess saw was that actually it's increasing as you go higher and higher. So based on this measurement, Hess concluded that there has to be radiation, but it's not coming from the Earth. It has to come from the outside of our Earth, atmosphere above. And he basically won a Nobel Prize by this discovery in 1936. In fact, we have now studied, since the discovery, we have studied the cosmic ray for now more than 100 years. It's actually about 110 years. And we now know a lot about the cosmic rays. And one thing that we know is that Earth has been bombarded by these high energy particles from our universe for millions of years. We are surviving here without any problem just because the Earth atmosphere is protecting us, as well as magnetic field is protecting us. So a big question from the Hess's time and up to here, so it's a century-old question, is what is the origin of this particle? So let's look at the nearby accelerator in our universe, the sun. The sun can actually generate high-energy particles during an extreme event like coronal mass ejections. But these particles have a similar energy to the lowest end of the cosmic rays, about 1 billion times higher than what we can see with our eyes, the visible light, but still this is low end of cosmic rays. The cosmic ray can actually have 10 to the 12 times, basically trillion times higher energy than these particles generated by sun just from time to time when very, very special event, extreme event happen in the sun. So what we are talking about is very, very extreme environment, much more extreme than our sun should be able to create this particle that the Earth is continuously bombarded. So what kind of environment can create this kind of particle? It has to be, again, very extreme. So maybe it is by the end of the star's light, the star can explode, and maybe that can they can create this high energy particle. Because when the star is exploding, this shock wave is moving with a velocity of 30,000 kilometer seconds. That is about 100 million kilometer hours. So that's about 1 million times higher than the speed limit of Highway 401. So this is a very, very extreme environment. So we think that it can accelerate the particle to the higher energy, much more so than our sun. Okay, sorry, I'm moving too fast. And then there's also a neutron star. This is a star that is 20 kilometer diameter. So that's actually about the half of the east-west length of Kingston. But they rotate as fast as 1,000 times per second. So it's very, very fast moving. And the gravity of this neutron star is 2 billion times stronger than the gravity on Earth. So this is indeed the extreme environment. And maybe particle can be accelerated in this environment. And then there's also, we know that there's something called binary stars, where the massive star is rotating around the neutron star that I just introduced, and the material of this massive star is slowly accreted by the nearby compact object, like a stellar black hole or the neutron star. And this creates a very extreme environment, and maybe this can accelerate the particle to high energy. And then there is a black hole, of course. There's a supermassive black hole existing at the center of galaxies. This has masses 1 million times more so than our sun combined, and then this can create the environment that is such extreme so that it can accelerate to the particles. The problem here is that we cannot use cosmic ray observation to find these sources. The reason why is because cosmic rays are bending inside the magnetic field. Again, these are charged particles. They are charged because they're so energetic, so the electron is already escaped. So they are highly charged particle. And so they are bending all over the place in our galaxy as well as in the universe because of the magnetic field. So if you trace the particle in one direction and you follow that direction, there is a good chance that you will not find the source there. So how do we solve this issue? The good thing is the physics works in Earth as well as in the universe. Just environment is different, but the physics principle works all the time. So we know that there has to be some interaction around the source area where this cosmic ray particle will interact and create subatomic particles. And among these subatomic particles, there are charged neutral particles such as gamma ray. Again, this is light with a high energy, and then neutrino, that is also charged neutral particle. Because these particles do not have a charge, they do not bend inside the magnetic field. So they straightly moving from where source is to the Earth. So if we can trace back their direction, then we can find the source. And indeed, we found a lot of sources. So this is a gamma ray sky. So basically, we put the pinpoint where we find the source. And this is the sky look like with the gamma ray, the sources that emit the gamma ray that is 10 to the 11 times higher energy than what we can see with our eyes in 1987. So that was one source about 30 years ago. But right now, in 2021, we have more than 200 sources discovered, all of them new discovery. And then because of these discoveries, we now know that all the extreme environment I just mentioned with a nice video created by NASA is actually emitting high energy particles and creating high energy particles and emitting the gamma rays. So this has been really, really exciting era for high energy astrophysics. On the top of it, now we are hearing from the ice cube that we now started to see the hint of high-energy neutrino sources. So these neutrinos are created by different processes in gamma ray. So by combining all this information can give us a lot of information about high-energy astrophysics and what kind of object can accelerate the particles to the high energy. So I would like to say, and this for me it's true, that we are living in a very exciting era of discoveries, and we are the closest humankind has ever been to answer the century-old questions. Where are these particles created? This particle that are energetic than what sun can generate, and the particle that have been bombarded the earth for millions of years. Maybe we can finally answer the question where these particles are created. So I think that's the end of my talk part.
Well, thank you so much for that introduction to where these kind of energetic particles might be coming from and the kind of things that you're trying to detect. But I asked you when we decided to have you on, it would be so cool to see where you get to do this exciting research. And so I know that you have some videos that you wanted to also share with us about where these really cool places that you get to do this research. I'm just gonna own that and take it away.
Thank you. So I wanted to actually show my lab, but my lab is still not existing because I just arrived at Queen's University last November. So meanwhile, I have a lot of pictures that I thought is pretty cool to share. So I volunteered myself to share this. So I am working on cosmic ray, gamma ray, and neutrino. And among these, I decided to just show my picture related with the cosmic ray experiment, just because it has a lot of cool pictures. So cosmic ray balloon experiment is what I'm going to show you. And I just wanted to walk through how we build the instrument and how we take data. So this is a balloon instrument, and you can see all this cool thing. Basically from balloon up to this car is basically provided by NASA. And the one that I built with my colleague is circled in that area. That is our instrument hanging there. And this is a much smaller scale experiment than the gamma ray and neutrino experiment that I'm working on. So the picture that you are seeing is more than half of our crew. Basically, this is less than 20 people working together to build the instrument kind of experiment. So you get to know a lot of things. Basically, you need to build everything from nothing. So you need to drill, you need to know about nuts and bolts and every detail of what you are building. And of course, you need to know each other very, very well, because you're basically building this and they have a flight in 5 to 6 years of time. So you get to know each other very, very well. And I really love all these ballooning people very much. So that was one of the motivation for me to share this. So how do you build a balloon experiment? First, you build the instrument. Again, this instrument is sort of big, but it's still human size. And actually, I'm going to share a lot of pictures from my 2011 CREST experiment. And that we, people measured by fun measuring the instrument in my height. So CREST is basically 1.5 Nahee length and 1.1 Nahee height. That's how we measure the instrument dimension for fun. Anyway, so it's a very, very recognizable size of instrument. So basically you build the instrument one by one, you test every single component to make sure that everything works, and you just assemble everything very nicely, and every cabling is very important, every nuts and bolts we had to drill very carefully to make sure that it will endure the environment that it's going to go through. And then basically what we do is we just test every single component. This is true for all the experiment for sure, but it's especially very important for the balloon experiment, because once the balloon, your instrument is in the air, there's basically nothing you can do if something goes off. So a single switch can completely fail the entire project. So redundancy is always important. Make sure everything is doubly checked. If you feel like there's a failure, make sure you have a multiple number of that is automatically switchable so that you can escape the failure mode. So the testing your instrument and then understanding the performance of your equipment is very, very important. So, but it's also very fun to study about the performance, because you need to know the performance to study unknown, which is the universe. And then once you are fine and you are confident that your instrument is very working fine and you understand all the performance, then what you need to do in balloon experiment is you need to put your instrument in space-like environment. The space-like environment we are going to put in my instrument is the 42 kilometer above the sea level. So there you only have 1% of air. So it's close to vacuum. It's not pure vacuum, but it's pretty low pressure environment. And then the temperature variation is pretty strong, because if the sun is shining directly to you, then you will heat up very fast, and there's no air to cool you. So you need to make sure that the thermal engineering is done properly. So basically we go to the NASA Plumbrook station in Sandusky, Ohio, and we put this instrument into this big large chamber that will be close the cap and then put it into the balloon-like temperature variation, as well as balloon-like pressure conditions, so that we can check that our instrument would work in a balloon-like environment. And then we go to the NASA's other facility, Columbia Scientific Balloon Facility, and then put everything, including the solar panel and the antennas, so that we can be sure that we can communicate and operate without any kind of problem. Our solar array can provide the power to the instrument. So that kind of thing is all need to be tested, and NASA has to approve that our instrument is performing as it should be. So those are additional tests over all the instrumentation tests. So if you pass all these tests with the flying color, then what you need to do is you go to the Antarctica. So this is the Air Force plane that we use. Basically, you go to the Christchurch and go to the Antarctica in our case, because we are going to McMurdo Station. So it's about 7 hours of very, very noisy flight. And then you go there, and then hopefully we arrive to Antarctica. So you may ask, like, why are you going to Antarctica? And there's a good reason. Other than Antarctica being very exotic place, because Antarctica during the summertime, during the wintertime as well, but especially in the summertime, Antarctica, first of all, the sun does not go down. So if you arrive in McMurdo Station in October, there is an indication basically saying that the next sunset is February. So there's no sunset in Antarctica during the summertime. During Antarctica summertime, in the wintertime in the Northern Hemisphere. That's really important, because we wanted to make sure that we can check the solar array and then power the instrument very nicely. Another thing is that around the time there is a vortex wind, which is basically circle-like wind that is surrounding Antarctica sky, so that when you are launching your balloon instrument in one location, it will have one nice round and it will come back, and that takes about 10 days. So in fact, on the left side, it shows the crest trajectory, which was 10 days. And good thing about that is if you're lucky and if you feel like you can go further and your instrument is still working, you can keep going. So for example, the next year is 2012, Super Tiger, this is a record-keeping balloon flight. Basically, they did that exactly what I said. So they had one circle and they thought that we can still going. So they went another circle and they finished with a 2.5 circle, and it took 46 days. So this kind of exposure is very important, because the high energy particles are very rare. So if you are taking longer time to take data, then you will have more of them. So this is very important aspect why we are going to Antarctica. So Antarctica, basically we are sleeping in McMurdo Station, where you are seeing on the left side, but our working station is Williamsfield, that is showing on the right side. And basically we commute. This is about 30-minute commute one way, and we are using this Evan Terra bus. And every vehicle in Antarctica usually has a very, very large tire, because there's no road. Basically, the snow packing, we make a road based on the snow packing. There's a lot of infrastructure for that. All right, so once you arrive in Antarctica, your instrument was flying and shake and all that user delivery issues. So we need to make sure that it actually worked as nicely as it worked before. So we need to keep testing our instrument. And if your instrument was testing nicely, what you do next is basically waiting for the good weather. This is very noisy, but this was one of the condition to stormy weather that we have, and we had to evacuate from the field station. So you keep waiting for the good weather, and once the good weather comes into you, then you basically move to the launch pad. This is a boss, which is can actually hang the balloon and then connect it to the balloon with the instrument. So it can actually move our instrument without hitting anything. So it's again very big vehicle, and it can carry up to more than 1 ton of instrument with it. And then once everything goes all right, then basically you will launch balloon. So here is what you are seeing. So the balloon is basically filled with the helium. It kind of looks like it's only head heavy right now, but once it's in the low pressure condition in 42 kilometer, it will become a pumpkin shape balloon. And you kind of can see that there's a orange thing here. This is basically parachute. When we are terminating, which I will show you later, when we are terminating, this parachute is going to be carrying the instrument. So now what BOSS is doing is basically trying to match it so that the instrument will be vertically aligned with the balloon, so that the instrument will not be stressed out when it's released. So it was sort of moving around to make sure that the vertical line is remained. And when that happens, I think it will happen soon. Let's see, around now. So you can see that we need to have an absolutely gorgeous day when there's no wind whatsoever in the entire height that you are seeing. The balloon has to rise, because if there's any air movement, then it would be really dangerous. And now it is released. So that release seems to be very smooth for you, but actually the instrument gets a 5 to 8 G acceleration. So we need to build the instrument so that it can actually endure that. And you can see the balloon is moving, and there it goes, indeed, our crust instrument. And at the end of the, so what happens then, the crust will follow the trajectory I showed you, and we need to decide when we are going to end the instrument experiment. We wanted to end the experiment long enough so that we can take enough data, but then we also want to recover our instrument so we can reuse some part of our detector. So we wanted to terminate where it is easy for us to reach, so that if it is nearby McMurdo Station, that's great. If it's nearby South Pole Station, that's great. You don't want to drop your instrument in the middle of the ocean. You don't want to drop your instrument in the middle of Antarctic mountain area. So that's why we need to be carefully to decide where we are going to terminate. And once we decide where to terminate, basically what happened is there will be airplane flying there, and remotely controlled to basically press a button to activate the explosion, because there's explosion material connecting the parachute to the balloon. So once that material is exploded, basically the balloon will go up and then ripped. So you can see the ripped balloon is going down, and parachute is opened, and now it is going to be just keep falling from the 42 kilometer over the sea level until it hits the ground. And then when it hits ground, it looks like that. So you may say, oh my goodness, can you save any of that? And it does look quite bad, because also, you know, Antarctica has a lot of snow. So if you are getting to the recovery site too late, then it's kind of covered in the snow. But in fact, we could reuse most of our instrument. Now, the recovery crew, which is usually 2 scientists with 1 flight crew pilot, now need to chop up this instrument on site to make sure that it can fit into this twin otter that you can see on behind it, and so that we can recover all of them, because it's in principle we should recover as much as possible. And in fact, for crust case, we recovered all of them. And so that was sort of a very quick journey of how balloon instrument works, and that was again in 2011. And now I'm working on Helix, which is another balloon experiment, which was supposed to fly this winter, but COVID situation pushes everything behind. So now we are aiming to go for the Antarctica flight in 2021-22 flight, and crossing our fingers the COVID situation will resolve very quickly. So this is my picture of the instrumentation, how it should look in the flightway, and my collaboration. So thank you very much for your attention. I think that was the end of my talk. And here I would like to introduce the Queen's University's graduate students, Emma, Ellingwood. And I emphasize how important the tests are. If I didn't emphasize enough, then I should say this again. Test is super important. It's very important to make sure that your instrument is working perfectly, and then you know exactly how your instrument works. And Emma was an undergraduate at McGill when I first met her. And she was a brilliant student who was working on the beam test to understand the performance of some part of the instrument. So I was very, very surprised to see her at Queen's University, and at the same time, very delighted to meet her. So I would like to introduce Emma, and then she will talk about her journey related with high energy physics over generally on physics.
Thank you, Nahee, for that introduction. So hello, everyone. As Nahee said, my name is Emma Ellingwood. I am a first-year PhD student at Queen's in the physics department. And today I wanted to talk about the lab work that goes on behind the scenes of some of these high energy and astroparticle physics experiments that Nahee showed. As she said, I used to work on the same cosmic ray experiment as her during my master's. And my role in that project was to study a particular material that we were using to measure properties of the cosmic rays that pass through the detector. Really, all of my work was hands-on, where I sat in the lab working with equipment and building detectors. So I really want to give a glimpse into some of the work that makes these experiments function. And I also want to talk a bit about the work that I do now at Queen's, which now I've switched from working on cosmic rays to now working on a dark matter experiment. My slides are not changing. Fun. Okay, so here is a diagram of the helix cosmic ray experiment. This detector is specially designed to make accurate measurements of the mass of cosmic rays that interact with the different parts of the detector. So the full detector is made up of multiple separate systems which all work together to help us learn more about each cosmic ray that goes through it. So what I was interested in was this lower portion of the detector here, which is called the ring imaging Cherenkov detector. So when high energy particles interact with this material that we have on top, which I'll talk about in a second, light is emitted according to the Cherenkov effect. And the Cherenkov effect is similar to a sonic boom that a supersonic jet produces, except here this happens with light instead of sound. So what you measure, it produces this essentially a cone of light. And what you measure on these light detectors on the bottom is essentially a ring of light. And basic principle is that the faster that the particle moves, the wider this Cherenkov ring will appear. But there is a problem with this measurement, though, because of an effect that you might actually see quite frequently. So I will introduce that first. And that is refraction, which is how much light appears to bend when it goes from one material to another. So you might see this if you're looking at a straw in a glass of water and the part that's under the water appears bent compared to the part that's outside of the water. So in physics, we give this property a number and we call it the refractive index, which technically is the ratio of the speed of light in a vacuum compared to the speed of light in the material. But essentially it does measure how much the light will bend when it hits a surface. And so if we're relying on measurements of the Cherenkov ring and you have this refractive index that affects your ring size, then we have to know the refractive index very accurately. So I have a quick diagram. So if you have a material like this and your Cherenkov ring, if it's one material, will just appear like a straight line. But if you have a high refractive index material and then it goes to a low refractive index material, so for example, in our case, something called aerogel, and then it goes into air, then you no longer have a straight cone, it deviates slightly at the surface, and you actually get a bigger ring than what you expect. So the material that we use for this specific detector for helix is called aerogel. It's a really, really cool material that's super light. It's sometimes called solid smoke. The issue is that we do not know what its refractive index is exactly, or if it is different at different parts of the aerogel. That is where the group I worked with came in, and we said if we still measure this ring of light that's produced at the bottom of these sensors, but we use particles where we know their speed, then we can find out how much the light is bent because of this refractive index. So how do you get particles of constant energy? Well, you use your local particle accelerator. In this case, we sent a beam of particles at the material. Here is my virtual electron accelerator. And when you send electrons at the material, you produce your Cherenkov ring, and you detect this ring on some light detectors a fixed distance away. And the principle is that if your detector is always set up the same and use the same energy of particles, the size of the ring that you produce should only depend on the refractive index of the material at the point where the electrons interact with the aerogel. So if you see the light in all these detectors, you can use that information to determine the size of the ring and then calculate the refractive index from that. Now that sounds like a grand plan, but what kind of things does this actually involve as a student? Well, actually, there's a lot of small tasks hidden within here. So this was about 1.5 years, 2 years worth of work for me in a lab, slowly building up the detector so that we were able to make measurements as accurately and as efficiently as possible. So it involves a lot of trying out different equipment, making sure you know how it works, and then troubleshooting any problems before integrating all of these parts into a larger system. And I'm not doing all this work also just to get one number. We have 50 of these tiles that you see here, which are about 10 by 10 centimeters. And we measured the refractive index in roughly 400 points in each of these tiles, making multiple measurements at each point in those. So it takes quite a bit of time to take that data and analyze it. So as a student in this lab, you work as a student in the lab in this type of work, you work on many different things. One thing is figuring out all of your electronics and connecting it all together, making sure you know how to control the electronics and all the data you need. And there's also part of this project, which is simulating the detector to determine what you should expect from your experiment. And then also figuring out how you're going to analyze the data that you get out. Sorry, there wasn't a pretty picture of data analysis unless you like looking at code. If you build everything carefully, then the result you get is a detector that you are confident works properly, which will essentially allow you to press a start button and that it will take data for you. So in this case, the way it was set up is that it collected many snapshots, about 100 of this ring. And then the motors that you see there move the aerogel so that since the detector and the beam are fixed, if you move the aerogel, the beam is going to go through a different part of the aerogel that might have a different refractive index. And so we did that and kept moving the aerogel in sort of a grid pattern to measure it at all these 400 points in a single aerogel tile. And then we switch tiles and repeat. So I don't actually have a picture of the end result on my computer, but essentially what you build is a map that will tell you the refractive index at almost any point in each of these tiles, depending on where a particle goes through the material. So we give this information to the experiment so that they can tell what the exact refractive index is where a cosmic ray goes through the detector at that point. So with all that information, I'm actually going to change gears a bit and transition about how the skills and type of work that you do in one experiment can be just as useful and relevant in a different experiment. In this case, it is going from doing lab work for a cosmic ray experiment based 40 kilometers above ground, which I did for my master's, to looking for working in a lab looking for dark matter 2 kilometers below the ground. So yet again, as a student, I do not work directly with dark matter search, but I work on a small part of the detector itself. And so I just want to give a brief glimpse into a specific project that I'm working on, which is looking at another property of a transparent material in this dark matter detector. So I still work in a lab, but we're looking at another material and different properties. The type of material that I'm talking about in this case is called a wavelength shifter. Where these come in is that you have two parts to many of these kinds of detectors, material which emits light when a particle interacts with the material, and then the light detectors used to detect this light. Certain light detectors have a lot of trouble detecting low wavelength light like UV light. Our eyes are not capable of seeing UV light either. The problem is that in some cases, the light that these particles emit when they interact with the material are in this UV range, so you can't detect it directly. So what we do is we put a layer of this wavelength shifting material between the light and the detector. So the atoms in this material absorb the light at a shorter wavelength and then emit the light at a longer wavelength. So the choice of the material that you use depends on a few factors, but one of the key ones is that it readily absorbs shorter wavelengths of light and that the light that comes out is a wavelength that your light detector can easily see. The issue is that some of these experiments I'm talking about, these dark matter experiments, run at very cold temperatures, and it turns out that how much light these materials emit and how long they emit it for actually depends on the temperature. So what we do in the lab is we use something called an optical cryostat, which is a system designed to cool to very low temperatures and also lower the pressure within the detector, or what we call pulling vacuum. You put a sample in and pull all the air out as much as you can and get it to the right temperature. And then you flash an LED at it, which emits UV light at it for a couple nanoseconds. So you collect that light that comes out after it passes through the material, and then you repeat the cycle a few thousand times really quickly. And you can take all the data and look at how long the light detector saw those pulses on average, and use that to calculate how long the light pulse was detected and how much light was detected. Then it is a matter of lowering the temperature of the detector and then repeating all these steps again. So we test the properties of these materials from about room temperature down to about 4 Kelvin, which is minus 269 degrees Celsius. And I thought I had another slide, but I guess I didn't. So I suppose that's the end.
Cool. Well, thank you so much, Emma. And Nahee, please, I know that you're going to come back now. And so we've had a number of questions for both of you. It was really interesting to hear about the kind of works that you do, Nahee, where you get to do it. And then like, I was thinking when you were speaking of like, what is actually going on in the detector? And so it was so cool, Emma, to then hear from you about the kind of work that goes into actually making that. And so, like I said, we do have a number of questions, and I do welcome any more questions from the audience. We see that some of you, and you're saying thank you for the great presentations. So Eduardo asked, Nahee, this question's for you. Well, maybe I'll ask my first question first, which is 1987, you see your first one of these cosmic accelerators, and then 30 plus years later, you now have over 200 of these detected. I'm just trying to think of like what changed? Why was it, why do you go from the first one being detected in 1987? What allowed us to then see so many now today?
That's a very good question. So the first, I hope that I have a picture, but unfortunately we don't have. So the first detection of the high energy gamma ray sources was detected by Whipple telescope, which is located in Tucson, Arizona, USA. And that was sort of the first generation telescope. It was a single telescope, and the design of the telescope was not as mature. Well, it was working, but anyway, that was detecting a single source. And then now we confirmed this technique of imaging Cherenkov, atmospheric Cherenkov actually works. Can I share the screen?
Yeah, I think that would be great.
Yeah, just because I have a great picture of imaging Cherenkov telescope. So that was the first generation telescope. And after that, after successfully detecting a source, now we confirm what the source actually looked like, and we could build a better instrument. So right now, what is currently in operation is so-called second generation, first generation, second generation, depends on person, but I would call second generation instrument, where, Whipple was only one telescope, but for example, the Veritas, it's again in the Tucson, Arizona, is a 4 telescope, and then the focal plane is a much better focal plane. So the system has improved. So basically we moved from 1 source to 200 sources by improving the detector. So right now we are sort of in 200 sources level, but the next generation, the third generation telescope, the Cherenkov telescope array now, which is going to have up to hundreds of telescopes over something looking like that. And actually, in fact, that we have 3 different style of telescope to cover a lot of different energy ranges. So that will also boost our number of sources we will detect a lot too. I would not call the number, but I'm pretty sure it will be more than 2 or 3 times increase of number of sources. So in short answer is that by improving your detector.
That's really, really cool. And I guess you learned so much from that first one. It makes sense that then you can like capitalize on that.
That's right.
So then a related question from Eduardo, which maybe you have a slide that you can bring back up. When you then showed the all sky map of where these were being detected, he asked, what information can you learn about the way that they're distributed? It seems like there's a lot of them oriented around like the middle. Why is that? And so yeah, what do you learn about the location of this on the map?
That's a very, very good question. So this is a map is shown in the so-called galactic coordinate. So what that means is this horizontal line that you are seeing is basically our Milky Way, how it looks. So basically you are seeing a lot of concentration of sources in here just because there's a lot of high energy accelerator in our galaxy. So those sources will be located mostly in the galactic plane. And then outside our galactic plane, then now as you go this way or that way, you are going outside our Milky Way. Now you are starting to see the red dots, which is actually the galaxy outside of our own galaxy. So this is a so-called extragalactic sources, which is all basically large galaxy style. And a lot of things that we are seeing is active galactic nuclei, which has a supermassive black hole in the center of the galaxy. So yes, the location basically showing you the whether it's galactic source or not, and then it's not always the case. For example, here you see that's a starburst. There's one Perseid nebula. Sometimes there's a small sources that is a little bit off galactic center, galactic plane, but still part of the galaxy. So this is where it's very important for us to utilize the information from traditional astronomy, like optical observation or radio observation, and combine all this information with a high energy observation to figure out where is this source and what is actually accelerating the high energy.
Really cool. So another question was from Nancy, who has joined us before for other Ignites, and she's very familiar with looking for neutrinos from deep underground in SNOLAB. And so she was wondering, is it necessary to be deep underground at a place like SNOLAB, or is it possible to learn about neutrinos without being deep underground? Like, are you looking at neutrinos with these balloon experiments? And how do you, if so, how do you eliminate like interference or background?
Right. So first of all, for the people, a lot of neutrino detectors are underground just because there's a cosmic ray that I just described, right? And which is great source and then like the scientific motivation for me, but it actually is creating unnecessary signal to study the neutrinos. So for example, ice cube's case, it's underneath like a 1.4 kilometer underneath, so that all this ice above the ice cube detector will be absorbing and then will remove some of the background coming from the cosmic rays. And so there is a balloon experiment called the ANITA experiment, which is studying very high energy neutrino, and then they are using balloon. And in that case, they are using quite different technology to study the neutrino signal. So basically they are looking at the neutrinos making a shower in the atmosphere and radio signal coming out of that. So in that case, there's not a lot of differences, is that the neutrino that you are looking at is much lower energy than the neutrino that ANITA is looking at. So the background there is much, much smaller. So I hope that answers the question.
Yeah, and then there's a question for you, Emma, particularly about the aerogel, and this is from Tony. It's the aerogel that you showed, like you're hanging it vertically. And so the question is, can you find differences in the refractive index, possibly from like a vertical distribution where it's probably denser at the bottom just from being hung? Or do you not see that kind of subtle differences from one place to another in the aerogel?
I'm not sure I completely understand the wording of the question.
Well, I guess like not like a more general question is, what kind of variation do you see in the index of refraction from one part of the aerogel to another? Because you said you were looking at like 400 places in the aerogel. It's
about 0.1%, maybe 0.2% difference. So they're very small changes. But if you're trying to accurately measure these cosmic rays and their energy or their mass, then you really do want to know this number very precisely and to that kind of precision.
And I guess related to Tony's questions are, do you see, like, is there a trend? Is it just randomly oriented around the aerogel, or is there some trend that maybe like the higher index of refraction is like more lower in the aerogel just from like being hung?
Well, it's not necessarily because when the aerogel is made, it's actually flat sort of horizontally. So it's not necessarily that if you have the tile sitting vertically that it's heavier at the bottom. But what you do see is that you see that the refractive index tends to vary kind of smoothly across. So it depends on how the tile was made and even the time of year that it was made, oddly enough.
Really?
I don't know too much about it, but I remember hearing that.
That's really cool.
So it depends on a couple different factors, mainly about how the aerogel is made, which I wasn't directly involved in. I just did the measurements.
I see. And there was a question from Eduardo again, is total internal reflection considered or relevant to these detectors? Does that happen inside the detectors?
For the energy that we were using for our tests and for the specific material, it doesn't exactly matter. It would matter more if we were using a higher refractive index material, then that is definitely something you have to consider. But at this refractive index, it's not as important.
I see. Cool. There is another question for you, Nahee, which is in that plot that you were showing of the distribution of points, it seemed like, let me just word it correctly. It seemed like there was lots of gray sources in the galactic plane and there was lots of red sources outside the galactic plane. Is that a real effect or is that like a detector bias just from where you're looking? Is the detector capable of looking in different places?
Right. Let me just share it so that we can talk while looking at that thing exactly. So yeah, that's really a good question. So this color indication is what is used in the TEDCAT UCChicago.edu, which is basically a collection of all the TeV gamma ray sources. So you can go into a little bit detail. So the color code is basically depending on the source classes. And the gray one is, if you look at that, you can see dark UNID other. So what that means is this is unidentified source. So basically, in short, what that means is we don't know what it is, which is interesting scientifically. So basically, as I said before, we are combining all the information that we know about that source reason. Still, what we are seeing in the TeV gamma ray does not really matches with what we are seeing in the low energy like radio to optical. One of the reasons is just because the optical and one of the reasons actually is that there's a lot of information that is missing. The astronomy is not covering the sky with the great exposure for everywhere in the galaxy, for example. So there's a little bit of a lack of information. And the other thing is, again, remember about the hands. So some object that is creating a high energy gamma ray is not necessarily very bright source in the radio or optical. So we do see the gamma ray sources, but we just cannot find the source of that particular gamma ray sources just because it's not clear how it is related to the known object in our galaxy around the particular region. Either that or there's so many sources there and our current angular resolution, how well we can localize a source is not good enough for us to figure out whether it's A or B or some combination of that. So that's why there's a lot of gray dot, which is actually about, I think, 40 to 50% of what is discovered in the galaxy is currently classified as unidentified source, and we don't know exactly what is creating this high energy gamma rays. So this is going to be something that we should revisit with the next generation telescope to look that has a much higher angular resolution and really do the much better study.
So I have, I think, one more question for each of you, and I'll do Nahee first, which is from Nancy. What, on that beautiful, nice day that you launched CREST, what was the temperature? It looked so sunny and nice.
I will tell you once. So the thing is, this is winter time in the northern hemisphere and the southern time in the Antarctica, right? And then again, sun does not go down. So in fact, it was very balmy. Without wind, actually it's pretty warm. I still remember in one of my colleagues in Chicago was saying that, Chicago is colder than Antarctica right now. So, that is a lot of the temperature differences. But again, it doesn't mean that Antarctica is really warm during the summer. It's just you feel warm because you are mostly staying indoor. And then when you go outside and excited, there's a sun to warm you up. So I don't remember exactly what was temperature. It probably was -10 or something, but it didn't really feel like that, especially because we were waiting for that good weather for like 2 months.
Right. I have to say -10 doesn't bring the word balmy to my mind, but that's great to hear. I guess that's you guys are easily impressed with warm temperatures. But and then the last question I had for Emma was, do you have any, I'm just curious to know like what your thoughts are. Like you talked about doing both the work with Helix and then going on to do the work with, I think that was Deep. I'm curious, like, what's that experience like as a student, like being able to go to a very different lab? Like, do you find you're learning all new skills, or are there like lots of ways that you're bringing your past experience into this new learning environment?
Well, I would say a lot of the actual lab equipment that you see and a lot of the instruments that you see are actually quite similar. I use similar electronics, similar light detectors to what I use. They might have different purposes. For the cosmic ray stuff, I didn't necessarily look at the temperature of things, but now I do. I don't use particle accelerators for my current work, but I used to. But there are still a lot of, as I said, like electronics, general techniques for particle detection that are really transferable between the two.
That's really, really cool. Well, I want to thank you both, and I also want to invite maybe Kevin and Elise to come back on and share the video, and we'll just say kind of one last thank you to everybody. And I didn't see any other real questions come in for you guys, Kevin and Elise, but I just want to thank everybody again for what was a fantastic night. It was great hearing from all of you. Thanks to everybody at home that was joining in. I hope you guys had a lot of fun and were maybe inspired about some of these different ideas that we heard. And I definitely want to find out how I get myself into Kevin's lab and start running around. I'm very flat-footed. I'd love to see how you can tell about that with and without my insoles. But yeah, so thanks everybody, and have a great night.
Thank you very much. Welcome anytime.
Thanks.